Homomorphic encryption. It's really the holy grail of cryptography, right? The ability to compute on data while it stays completely encrypted. But for us engineers, taking that beautiful theory and making it work in the real world, well, that's a whole different ballgame. It's a serious performance battle. And this quote right here, this is really our North Star for today. It cuts right through all the complex math and gets to the heart of the matter. Because look, if we can't make homomorphic encryption fast enough to be practical, it just stays a cool idea in a research paper. So today, we're going to put on our engineering hats and get into the nuts and bolts of how this stuff actually gets built. So, what is this big performance hurdle we're talking about? Well, at its core, the mathematics that let you do something as simple as adding two encrypted numbers, it's incredibly heavy. It's computationally expensive. So the question for an engineer isn't, can we do it? The question is, can we do it fast enough to be useful in a real application without bringing the whole system to a screeching halt? Now, the very first place we have to tackle this performance issue is right at the beginning, in the setup. Before you even think about writing a line of application code, you have to choose your parameters. And this isn't just flipping a switch. It's a huge strategic decision that's going to define the rules for your entire system. You can think of these three things, security, depth, and precision, as the main tuning knobs you get to play with. But here's the catch. You can't just crank them all to max. They're all interconnected. Turning one up affects the others, and most importantly, it affects the overall speed. It is a constant balancing act. And this table really lays out those trade-offs for you. You want more security? Okay, but your operations are going to be slower. Need more computational depth? And that's just a fancy way of saying you need to do a whole chain of calculations. Well, performance is going to take a hit. Think about it. Just adding two numbers is a pretty shallow operation. But training a machine learning model on encrypted data, that requires a lot more depth. Same thing with precision. So your job, as the engineer, is to find that perfect sweet spot for whatever you're building, giving it just enough of each without totally killing the system's performance. Okay, so with all those constraints, how do we start to claw back some of that performance? Well, that brings us to what is, without a doubt, the single most important tool in an HE engineer's toolkit. It's called batching. The idea behind batching is actually pretty simple and, kind of brilliant. It's like this. Instead of sending thousands of individual packages one by one in tiny little boats, what if you could just pack them all into one massive cargo ship and send them all at once? That's what batching does. We pack thousands of different data points into a single, big ciphertext. So here's what that workflow looks like. You pack all your data together, you do one single encryption, and then when you perform a computation, say an addition, it gets applied to all 1,000 of those data points at the exact same time. Then, one decryption at the very end, and bam, you get all your results back. It's that parallel processing that gives us this huge efficiency gain. And let's be clear about the kind of improvement we're talking about here. This isn't a 10 or 20% speed up, no way. When you use batching effectively, you can see performance gains of over 100 times, 100-fold. This is the technique that takes an idea from being theoretically possible to actually being practical in the real world. But, there's no such thing as the free lunch. Packing all that data together for batching is amazing for efficiency, but it introduces a very real, very physical problem: system memory. And this, right here, might be the biggest understatement about homomorphic encryption. The data structures we're working with are just enormous. This isn't some small detail you can optimize away later. It's a fundamental property of the technology, and it will quickly become your #1 bottleneck if you're not careful. This chart really shows you why. That tiny little bar on the left, your plain text data, well, once it becomes a homomorphic ciphertext, it just explodes in size. I mean, we are talking about a data expansion of thousands of times. So yeah, batching is incredibly powerful. But when you're packing thousands of values together, you have to be able to manage these gigantic ciphertexts in RAM. And that is a hard physical limit you just can't get around. So all of this brings us to a really critical point. All these different techniques, choosing your parameters, your batching strategy, how you manage memory, they don't exist in a vacuum. They're all deeply connected pieces of a much larger system. And that's why you have to understand that performance tuning in HEE isn't something you do at the end. It's not an afterthought. It has to be a core part of your system's architecture from day one. The security parameters you choose will directly affect how much memory you need.
Your batching strategy basically defines your entire data pipeline. You can't just write the code and then try to make it fast later. You have to design the entire system around the physical realities of homomorphic computation.
So let's wrap up with the key takeaways for any engineer looking at this space. First, balance is everything. It's a constant trade-off between security, depth, and speed. Second, batching is your superpower. It's what makes this all practical. But third, memory is the wall. It's the hard, physical constraint you always have to design for. And finally, remember that it's all one big system. These aren't just a collection of clever tricks. They're integrated components, and performance has to be the foundation of your design, not just a feature you add on later.
So that leaves us with one final question to think about. When you look at this intense balancing act between privacy and performance, which industry out there, maybe healthcare with its sensitive patient data, or finance with its transaction records, which one do you think has the most urgent need to solve these challenges and really unlock the power of fully private computation?